which is a fusion reactor that's currently being built in the south of France, is to make a star here on planet Earth. To make a star, we have to burn our fuel in the plasma, and ITER is going to do this at 150 million degrees. That's 10 times the core temperature of the sun. It's the hottest place in the solar system. So how do you then contain that star? Just imagine trying to put 10 suns in a box without the box just instantly vaporizing. Well, that's where superconductors come in. Superconductors can generate very large magnetic fields that are capable of trapping these stars without melting themselves because they have no resistance. Now, because of this, superconductors are already used in applications like MRI body scanners in hospitals to particle accelerator in CERN. However, there's a limit to the maximum magnetic field we can get out of a superconductor, and that's called the critical field. Now, this places a ceiling that limits what we can do. So we want to raise the ceiling, the critical field, to be as high as possible. How do we do that? Well, in the past, Durham scientists have successfully increased this critical field of niobium by a factor of 4, from 0.8 to 3 Tesla. We achieved this by reducing the size of the grains of the materials by 1,000 times, from micrometers down to nanometers. The result was a nanocrystalline, high-field superconductor. However, this material had a very, very low operating temperature. Now, just to give you an idea, ITER superconductors is going to work at 4 Kelvin, that's minus 269 degrees. To cool it down, we need to use vast amounts of liquid helium, and that's very expensive. It's the same price per liter as whiskey. Instead, we like to work at 77 Kelvin, because then we can use liquid nitrogen, which is much cheaper as the price of milk. So let me now tell you where my project comes in. I'll be working with high-temperature superconductors. These are materials that normally work in the cheaper liquid nitrogen temperatures, but at these temperatures have relatively low critical fields. I'll then take this material and make it nanocrystalline, and by doing so, increase the critical field of the material so that we'll have a high temperature as well as high field superconductor for fusion technology. Now, to finish off, I'm going to show you how ignition is going to work in the plasma of a fusion reactor. Our plasma is contained inside this fluorescent light bulb, although it's on the smaller and cheaper scale compared to ITER. As you can see, there are no wires or plugs leading from our plasma. Now, because we have a small plasma, we can use conventional magnets rather than superconducting magnets. Now, I'm hoping that when I hit the on switch, the magnetic fields generated by these magnets is going to make our plasma shine. But like all good experiments, there's no guarantee that this is going to work. That's